Okay, so this is the fourth run through this video. Let's try this again. All right, so we're talking about fusion and fission today in class. Nuclear chemistry, right? So we're talking about the fission or the fusion of two nuclei. Today we started out in part one with fusion reactions. So when you think about fusion, you're fusing things together, you're joining them together. So in class today, in the activity that they did, and I will post this activity online if you want to look at it. Okay, it says in fusion, atoms in a plasma state are heated up. It gives them enough energy to collide and stick together. Once the atoms collide, they release a ton of energy. In this activity today, the microwave is going to provide the energy. So here we go. What they were given today was 2 cookie dough samples, okay? And they had a scale and a piece of parchment paper. They placed the parchment paper on the scale, zeroed it out. Then they took one of their nuclei, right? This is supposed to represent a hydrogen nuclei, and they weighed it. This one weighs about 10.7 grams. Then they had to convert that into kilograms. So they divided that number by 1,000. So 10.7 divided by 1,000 would be about 0.0108 grams. So that's the mass of one of the nuclei, right? Then they got another sample of hydrogen, another hydrogen nuclei, and they weighed that one. That one's about 11.1 grams. Okay, and they recorded that, so 11.1 grams. And again, it needs to be in kilograms, so divide that by 1,000. So it's about 0.0111 grams. So these are supposed to represent 2 hydrogen nuclei. These are called isotopes, right? These are isotopes of hydrogen. That's what they represent. That's what we were modeling. So I'm going to take these isotopes, and the next part of the procedure said to put them at about 2.5 centimeters apart, which is approximately an inch. And then I'm just going to stick them in the microwave. A really gross, disgusting microwave. I'm going to put them in here. I'm going to put them in here for about 30 seconds. And we're just going to let that set for just a minute. Okay. Now remember, the purpose of the microwave was to provide energy. Okay. You're trying to get the atoms or the nuclei to collide with each other. And they have to have enough energy to do that, to fuse together. Okay. And when they do that, the next part of the reaction or the next part of the procedure says, be careful not to overcook, which I've done that several times today. So I'm going to check them. And once they cooked their cookies, the next thing they had to do was, finally, I didn't burn them. Okay, so if you're doing this at home, 35 seconds, it's the magic number. Okay, so they cooked their cookies in the microwave, and you can see that. Who knew? Microwave cookies, right? Did you guys know this? Anyways, you can see that the cookies do what cookies do in the oven as well, is they tend to fuse together if you put them too close together, right? Just like nuclei fusion, if the atoms have enough energy to collide, they will fuse together. The nuclei will fuse together. The next thing that they did, they let that cool for a good minute or two. In science, if you don't let things cool off before you try to weigh them again, because of like heat convection currents, it causes the weight to be inaccurate. Sometimes they will weigh more than what they're supposed to. Okay, so I'm going to try to let that cool off enough. And remember from earlier, I think it was 10.8 grams and 11.1 grams. So what would that be? Like 21.9 total is what we kind of started with the 2 individual atoms or isotopes. So now we're going to stick this back on the scale and see what we've got. And remember, we already accounted for the paper. So this is saying 20.6 grams. So we started with a total weight of like 21.6, like when we added both of those isotopes together. This is, or 21.8, this is saying this is 20.6. So we lost about 1.2 grams of mass. And again, if you're doing kilograms, that would be like 0.0012 kilograms. was lost in the process, okay? Now, of course, we know you can't lose mass in a reaction. What do you think happened to the mass while it was in the microwave? Probably it was lost as water weight, right? The microwave excited those water molecules and it caused the water molecules to evaporate, so we didn't really lose it. But for our purposes here, we're going to say that the mass was converted, and specifically in nuclear reactions, mass gets converted into energy, okay? So then as a class today, we went ahead and talked about some of these questions together. We said they had to draw it out. They had to do a drawing of the cookies before and after. And then they looked at this equation right here, which is just the nuclear fusion reaction that occurs in the sun, where you have a hydrogen 2 isotope that mixes with a hydrogen 3 isotope, and it creates helium and a neutron. It gives off a neutron. And there's energy that gets released in the process, a lot of energy, right? So, and it says, do you see any similarities between your drawing and the actual reaction? Yeah, they did. They had 2 isotopes and that fused into 1 cookie, okay? So yeah, there were some similarities. They went through and they looked at number 2. What did you notice about the number of protons and neutrons on both sides of the equation? Well, if you're looking at this, and that's one thing that we pointed out today in class, if you're looking at the numbers of, remember, protons are the numbers on the bottom. On this side, the proton number is 2 total. And over here, it's 2 total. How about the mass? Let's just talk about mass at the top. Mass, 2 plus 3 is 5. If you look at the other side of the reaction, 4 plus 1 is 5. So the protons and neutrons in the reaction, the numbers should be the same on both sides, okay? You can't lose things in nuclear or chemical reactions, right? So the numbers stay the same on both sides of the equation. They just switch places. They go to different areas. Name 2 ways this experiment is like a fusion reaction. Well, first of all, if you're talking about fusion, the cookies fuse their nuclei together, right? They fuse, they join together. Another way that you could say this is like a fusion reaction is that we did show that mass was lost. But we probably know that was water mass that was lost from the cookies. Okay, so number 4, name 2 ways in which this experiment is different from fusion. Well, first of all, it's cookies, right? We were using something physical, okay, to model very, very tiny little particles. Another way that this is very different from fusion is that we know that energy had to be added in through some physical source like a microwave. In nature, the energy is just, it comes from reactions around it, okay? The energy is just absorbed by some other source, okay? But we had to actually put energy into the system. Number 5, it's going to ask you here on number 5 to use the Einstein equation, E equals mc squared. And you're going to have to calculate based on the mass that was lost. So you need to go back and calculate how much mass did we lose from the beginning to the end, and then use that mass that was lost to calculate the energy that was released during this reaction. Because just like when you're fusing nuclei together with the sun, you're going to have mass that gets turned into straight energy. Okay, so how much energy would have been produced based on this cookie reaction? Okay, so go ahead and calculate that. Use your E equals mc squared and see if you can calculate the energy that was created by the mass that was lost from the cookies. And then finally, they had to use this energy table to answer question number 6. Okay, so they had to use this table to calculate and to estimate how much or what could the missing mass be used to supply energy for according to the chart? Based on the mass that you lost with the cookie reaction, how much or what could you do with it? What could you do with that energy? Okay, so take that table, figure it out. That's what we did to represent fusion today. We'll talk about fission a little bit later.